Science is for everyone. Science is for everyone. C2ST. 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 Chicago Council on Science and Technology. C2ST. 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 Chicago Council on Science and Technology.
Quantum science is the physics of smallest scale. Quantum information science deals with acquiring minuscule amount of energy or information from quantum systems utilizing quantum sensors. And we can harness those to look for certain phenomena, signature, or dark matter in our case. Hello, everybody. I'm Roxana Khatiora. I'm a professor at Illinois Institute of Technology, and I'm also a scientist at Fermilab. I work on dark matter detection using quantum sensing. So today I'll be talking about what quantum sensing is a little bit, and I will take you in a virtual tour of our facility, our lab at Fermilab, and you'll also hear from a couple of our scientists there in my group.
One of the problems plaguing the quantum information science community is that the fundamental bits of a quantum computer are very sensitive to environmental noise. And that's a problem for them because you really want information to be retained so that you can do all of your calculations and so on and so forth. But one of the really nice things is that if you turn the coin over, it means that those sensors are potentially, or those fundamental, we call them qubits, fundamental elements of quantum computers, those may be more sensitive to certain kinds of interactions, say dark matter, than other detectors that we have built are. And so the idea behind this group and this group's efforts is that we want to take the massive amount of progress in the quantum computing field over the last few decades, and turn that into, flip it on its head, and turn that into a potential detector or sensor for dark matter scatters in the lab.
So sensing is basically acquiring information that you want, right? So quantum sensing is detecting extremely small amount of energy, magnetic field, temperature, anything that you're measuring with quantum technology and tools. So that's kind of how I would define it. And so you probably have heard of qubits, which are these artificial atoms, and also the building blocks of quantum computers. These are the broadly used quantum sensors, and that's what we use to look for dark matter and detect dark matter.
A sensor is something that can take a signal of energy and transduce that into something that a computer can process in the most general sense. And so that might be something like you've got a target material, so some crystal, and you've got dark matter or some other particle coming in, and it slaps an atom and produces some charge or some vibrations in the crystal, and you want to read those channels, either the charge or vibrations or whatever it may be. You want to read that out and digitize that signal and do some analysis on it to learn about the particle that came in and slapped your target.
Quantum sensors have advantage over traditional sensors in mostly two ways. One is they have extreme sensitivity to measure any physical observables that we discussed, like magnetic field, temperature, energy in general. On the other hand, they also have advantage over how fast the measurement can be done. So typically the quantum sensors would be able to do the same sort of measurement, get to the same amount of sensitivity in an extremely small, shorter amount of time compared to a traditional sensor.
We're talking a little bit about dark matter direct detection. We want to build a detector in which the dark matter particles can scatter, and then we can see it. The kind of sensor that we want to use, again, is from the quantum information, quantum computing field. And what that looks like is actually a very small chip of either silicon or sapphire with some superconducting metal plated onto it. And so if you look in here, in the center square, you can kind of see a little bit of reflective chip. And that's effectively our detector. And it has 6 qubits on it, so that and those qubits can read out or sense the very may be able to sense the very weak interactions that arise when dark matter bumps into the chip material. And then of course the chip is kind of installed in a housing that keeps it cold, and it extracts heat from it so that we can see the small amount of heat that's deposited when a dark matter particle scatters. And then there's a bunch of cabling that allows us to talk to the chip and read out the information from these scatters. And then all of that is inside this kind of cylindrical can here, which kind of provides magnetic shielding because the sensors themselves, the qubits, are very, very sensitive to magnetic fields. And so by surrounding it with this can, you can kind of expel magnetic fields and keep that inner region very quiet in terms of magnetic field.
So all the qubit devices are housed in this refrigerator. So this is not your regular refrigerator. This is called dilution refrigerator. And so it's one of the coldest refrigerators out there. It cools everything, all these devices, sensing devices, very, very close to absolute zero, which is the coldest temperature we can have in the universe. And so everything is at room temperature on top of the fridge. And so all these different plates that you see in the fridge correspond to various temperature stages in decreasing order. So you are going from room temperature to slightly colder on top there, even further colder down here, and then the coldest being here. So this temperature stage is very, very close to absolute zero, which is 0 Kelvin. So this is like a few millikelvin we are talking about. So very, very close to absolute zero. And so this is work of art, and it has taken engineers and scientists decades of work to come up with this kind of dilution refrigerator, because it's extremely difficult to get anything this cold to absolute zero, this cold close to absolute zero. So here what you are seeing is the sensing devices based on qubits housed in this plate over here. So this cools this device to very, very close to absolute zero. And as I mentioned, we do want the devices to be physically very cold because we want to avoid these background photons that is not good for our dark matter experiments and other sensing, like fundamental science experiments. So we want to cool this like this. And so here you can see other accessories also installed in this refrigerator. So the main idea is we sent out some known signal from top of the fridge. It goes to the qubit-based devices here, and then for sensing purpose, we can get information about the state of qubit by looking at the signal that comes out back. So whatever we send in, it changes a little bit depending on the state of the qubit, and we read it out back. And that signal that we read back will tell us, did the qubit state change? And the qubit state, if it changed, that means you had either dark matter activity or some sort of background that changed it. And so that's kind of like the core of sensing. That's how we do sensing with qubit devices. You saw earlier the warm refrigerator. It was open. It had been open for us to populate with the electronics, the qubit-based quantum sensing electronics. So here is an example of how it looks when it's cold. And so of course you can't see the inside, right? Like, so there's shield here, and right now it has a bunch of qubit-based quantum sensing apparatus inside, and it's cold. It's about 10 millikelvin or so very, very close to absolute zero.
Dark matter is produced very early in the universe, and so once we start to understand how dark matter interacts, we can then look back and say, okay, given how we know now, from what we can see, how it interacts, what effects that would have had on the early structure of the universe. And so I think what's really interesting about dark matter is the fact that, like, none of this stuff exists without dark matter, because in the early universe you have these minor fluctuations in density. Dark matter is there's way more dark matter than there is regular matter, and so you have all of these areas of slightly higher density of dark matter and slightly lower densities of dark matter, and so once you start to get matter around, it's going to gravitationally be attracted to the places where there are dark matter. And that's how you start to get structure formation in the early universe. Galaxies, yeah, so what would become a galaxy and eventually lead to star formation and eventually lead to the burning of the light elements into heavier elements that you need to create planets and eventually, humans. And so really, like, we wouldn't be here to study dark matter or anything if dark matter didn't exist or had way different properties than what we expect from our observations.
The universe is composed of a few different components, only one of which is the kind of, what we call baryonic matter, which is normal stuff, like us, what this room is made of, what the Earth is made of, all of the elements, things like that. That only composes a very small fraction of the total energy density of the universe, and as it turns out, is kind of outnumbered, 5 to 1-ish by another kind of matter that we don't understand, that doesn't, like to interact with, light. It really doesn't like to interact with things much or at all, except through gravity. And so we can see that using telescopes and a number of other methods to identify that there is some extra mass out there in the universe that's not the stuff we're made of. Now the hope is that we can actually detect that using, in a terrestrial detector, under the assumption that it interacts very rarely or weakly with the kind of normal baryonic matter that we're made of.
What is dark matter? We don't know what type of particle it could be. Some kind of composite object has been, for the most part, ruled out, so we really think it is some new fundamental particle. But given that we have, in the range of where a fundamental particle could live, that's something like 30 orders of magnitude. And we've, again, carved out, 3 here, 6 there, but there's a whole zoo of particles. For every different mass range, there's some different type of particle model that could populate that space and be the dark matter. And so really nailing it down and what that could be is what really drives me to keep doing physics.
Dark matter is kind of one of the biggest problems in physics today. Particle physics especially. We've, as a society, first identified that dark matter was a thing kind of in the early 1900s. So we really have not seen it interact with normal matter in a non-gravitational way for around 100 years now, which is a long time. So we finding it and seeing an interaction of dark matter in a terrestrial detector that we can conclusively say, these interactions are dark matter, would be groundbreaking. It would be the first time anyone has seen that conclusively, and it would help us work our way toward a more complete understanding of kind of the fundamental bits and pieces of matter and how they interact.
A couple things. One is that the alternative to particle dark matter is some modified theory of gravity. And personally, I haven't seen and I'm not aware of any model of gravity that can reconcile all of the different observational signatures, dynamics of galaxies, dynamics of galaxy clusters, the large-scale structure of the universe, and the cosmic microwave background, the temperature and isotropies in the cosmic microwave background. Modified gravity can't simultaneously explain all of those things, whereas the cold dark matter paradigm does, with one model, reproduce all of the observed phenomena. In terms of, looking for particle dark matter, yes, we've been doing this for maybe 2 decades now. Not traditionally, but historically, most of that effort has been focused in what's called the WIMP, weakly interacting massive particle space, which is, like I said, 10 to 1,000 times heavier than a proton, and we've had no luck there. That's right. But we don't know what type of particle dark matter could be, and to be consistent with observations of astrophysics, there's basically like 50 orders of magnitude where dark matter could live. And so that's a lot of parameter space to check, and we've carved out a good amount of parameter space in the 10 to 1,000 GeV, so 1 GeV is about the weight of a proton. In that space, we've carved out significant space, but that's 3 orders of magnitude out of the 30 where it could potentially live. And so building sensitive detectors that can probe different regions of that parameter space is going to be key for eventually discovering the dark matter particle.
Dark matter really doesn't like to interact, and so it's not, when we detect, when we detect dark matter, it's not going to affect, my mom's everyday life, right? She'll be very excited that we found it, and she'll be like, "Oh, there's my boy," but it's not gonna have a direct impact on the lives of people today, because it doesn't like to interact with what we see, right? But there, I would say, are 2 things that two caveats to that, right? So one, the search for dark matter is itself valuable. Finding dark matter is kind of a major milestone in understanding the universe around us. So that's the kind of academic answer. But getting there requires developing technology that doesn't exist yet, right? And so, for example, I mean, the work that we're doing, we're taking knowledge from the quantum science community and we're turning it on its head and trying to use it as quantum sensors for dark matter. But in the process, we are doing more research on the environmental interactions in these sensors that we can then turn back around and hand back to the quantum information community in such a way that they may be able to feed that into their design of their quantum computers, which then may lead to future kind of advancements in that field and in more direct impacts on society than knowing that there are a bunch of invisible particles that pass through us and exactly what they are, right? So there's really 2 different ways to see this. One is academic, like the hooray science moment, and the other is technology feeds forward into technology developed in the search feeds back into society. Yeah.
Even if dark matter, if there's no way to apply dark matter and harness its energy, which to me, it seems like a long shot because of how, the challenge in detecting dark matter is how weakly it interacts with everything. So maybe there's no direct application of dark matter, but the technology that we need to look for it and how we improve that technology and build more sensitive detectors can translate into many fields of industry. And eventually, developing quantum computers is something that will for sure impact everyone's day-to-day life. Maybe not in the next decade, but in the next 50 years for sure.
Huge portion of the matter content of the universe is dark matter. So by understanding dark matter, we know what the universe is made up of at the fundamental level. So this kind of addresses the curiosity, the fundamental curiosity we humans have. So that is really satisfying to understand our origin. And also, historically, what has been true is the application of dark matter or application of any particle, novel particle. Historically, what has been true is that its application follows its discovery. We find ways of utilizing it after it is discovered. Like if you look at electrons, protons, neutrons, their application came much later. It was not realized initially. And so the same probably will happen. We'll discover dark matter, and then we'll figure out application that's going to revolutionize the world. So yeah, it has innately, it's satisfying to know our origins and what the universe is made up of to begin with.
Will this lead to teleportation devices? And I'll say no with an asterisk, right? What is the asterisk? Well, an analogy I like to make for anyone who asks anything about whether dark matter will be useful is that right now, I don't think it's going to be useful. But if you think back 200 years, people didn't know that the electron existed. And now people are, have smartphones. People have all sorts of really high-tech stuff that allows them to do interesting things that people 200 years ago would never have dreamed of. And that scientists 200 years ago would have never attributed to the existence of an electron or the increased knowledge of an electron. So my asterisk is, I don't think so right now, but that is also because I'm a product of my time, which means that my knowledge is only based on what we currently know. And so maybe in 100, 500, 1,000 years, that picture may change. So.
Science is for everyone. Science is for everyone. Science is for everyone. C2ST. 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 Chicago Council on Science and Technology. C2ST. 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 Chicago Council on Science and Technology.
Wow, hello everyone. Thank you so much for watching our first ever video premiere in our last program on the Quantum Information Science series. Again, to ask questions, please visit our Slido page at slido.com. That's SLIDO.com, using the number 4146632. Again, that's 4146632. So much love went into this video, and I'd really like to thank the C2ST team, Dawn, Jake, Andrea, Sasha, and most importantly, our speaker, Raksha, and her awesome team at Fermilab. Speaking of our speaker, Raksha Katiwala is an assistant professor of physics at the Illinois Institute of Tech and a scientist at Fermilab. Currently, she is the group leader of a dark matter quantum sensing project at Fermilab, where she works with many scientists, postdocs, and students, and oversees several quantum sensing and technology development projects. She completed her postdoctoral training from Fermilab and University of Washington, Seattle, an axion dark matter experiment and qubit-based quantum sensors between 2015 and 2020. She received her PhD in physics from Purdue University in 2015 and received her undergraduate degree in physics and mathematics from Linfield University in 2008. She was born and raised in Nepal and moved to the US to follow her dream of becoming a scientist. Apart from her work, she loves reaching out to underrepresented groups, minorities, and institutions to talk about quantum sensing or career opportunities in science in general. Again, to ask questions, please go to our Slido page at slido.com using the number 4146632. Raksha, I'd love to welcome you to our Q&A portion of the program.
Thank you, Denise and the team. Hi, everybody. Glad to be here.
Awesome. Well, we all have some questions already queued up here. The first question asks, can you please describe your career path in physics?
Yes, so I actually saw that. And so this question specifically asked my career path. So I'm going to kind of like insert a little bit of personal touch. So as Denise said, I grew up in Nepal. And so I finished my high school there and I was on a way to medical school. And I was very interested in physics. And so I just wanted to, get a physics degree and be a scientist. That was my dream. And so the one caveat is that, in Nepal, there wasn't a whole lot I could do in terms of research in physics, like fundamental science. So I was like, okay, how do I do this? And then I started exploring all these programs abroad. And that's why I applied to these universities and small colleges in the US that give me or that had the potential to give me full scholarship. So I literally went to collegeboard.com and applied for in like several different universities and colleges, and then got full scholarship for physics in undergrad in this small liberal arts college in Oregon called Linfield College. And so that's kind of how I started my journey to study physics. And of course, I loved it. I got physics and mathematics double major. I completed that in 2008. And so I wanted to go to grad school, but I did internship at Fermilab, and I decided to take a year off and do further internship after my undergrad. And so I came to Fermilab and I did internship here in Higgs boson at that time. And I went to grad school after that in Indiana University and Purdue University. And so after grad studies, Denise told you guys that I did my postdoc in University of Washington in Seattle. And then I joined Fermilab, and in a couple of years after that, I started this faculty position at IIT and Fermilab. So my journey, other than the part from Nepal, is pretty typical of a scientist or a physicist in a physicist career. So yeah, it is a long journey, but it can be very rewarding if you love research and science. So yeah, that is the typical career path.
Awesome. Thank you so much for sharing that. I know that you and I talked about this in while we were filming the video, and it didn't unfortunately make it to the final cut, but I think it's really important to discuss your in general, the lived experience of someone who isn't someone who we think about when we think of a physicist or a scientist.
Yeah.
Can you talk a little bit about your experiences sort of persevering in a field where you didn't see yourself represented?
Yes, I can. Yes. So, traditionally, and I think this is changing a little bit recently, but it has been that, when we think of scientists or physicists, certain type of stereotypical picture comes in our mind, right? So it hasn't been really people who look like me or, a minority, right? So it has been challenging, definitely at many stages in my career. And so I just had to kind of, just keep at it. And I wanted to do physics more than anything. And so there were times when I did not feel like I belong in this area, but that didn't stop me from doing what I wanted to do. So I think things are changing a little bit, fortunately and hopefully, but not at the rate we would like to. One example is I went back to my undergrad institution when I was doing my postdoc, and I saw way more women in undergrad, physics majors than when I was there. I was literally like one of the 2 or 3 or, something like that. So I think that is changing. And here also in Fermilab, the group I have, surprisingly, we have more women postdocs and graduate students and undergrad than 5 years or 10 years ago. So I'm actually really glad this is changing, but yes, it hasn't been easy.
Awesome. Thank you so much. Yeah, I think discussing those lived experiences is really important.
Yeah.
All right, on to some other questions. There's some really interesting ones that I had not thought about, but this one asks, how does a regular computer read signals from a quantum computer?
Yeah, right. So so I like when you think of quantum computer, I want you all to think about quantum computer as not this like, you know, little form factor regular laptop that you think of. Quantum computer now still exists in this very delicate form. Like you guys saw the video where I gave you the tour of this lab. So literally what you saw, that refrigerator that I showed you for the quantum sensing devices that house those devices, quantum computers look like that. So quantum computers would have way more qubits than what we have been using in that refrigerator. So it will look way more populated with these qubits and accessories. But the general idea behind that is, so for quantum computers to work, you want to prepare these qubits in certain state and you want to maintain that. So think about quantum computers as this delicate system of like qubits in certain states that you know. And so and you want to preserve that. And so think of this as like this delicate cold system that exists in a refrigerator, like I showed you. And so reading out signal, or I call it signal, but when you say reading out quantum computer, you're reading out what the states of the qubits are. And so that is a very standard protocol that has very standard things that can do that. And so you just read it out through those standard, well-established protocols in quantum science. And then you just like digitize the analog signal while you do that. And that is pretty standard method of data acquisition. And you just read it out with your regular computer. So that's kind of the gist of it.
I see. Okay, so on that note of a quantum computer being really small, I think that was a really good precursor to the next question, which asks, why does a qubit have to be so small?
Yeah, so yeah, tell me about it. That's one of the problems that we have too. So we'd love for the qubit to be bigger. That will solve a lot of our problems. But turns out that is a really good point. So, you know, like the qubit is this fundamental building block of quantum computing. And so somehow, like, you know, when you are talking about these superconducting circuits like qubits, it's based on like superconducting superconductor. And you know, it's the fundamental circuit that you can produce using superconducting technology. So by definition, it's actually really small. So and there are also these fabrication parameters. In order for a qubit to be qubit, you have to work with some certain fabrication parameters, and that kind of limits like how big you can make it. So it kind of comes from that kind of constraint too. So one way of getting most out of qubit is to use multiple qubits. So, you know, since we can't make individual qubits big, we might as well use a lot of them. And so that's kind of what we try to do in quantum sensing. And also in quantum computing, we do, try to use many qubits. So good question, though. That was a tough one.
Yeah. Just out of curiosity, have you ever made a qubit, and how long did it take you?
Oh, I have not made a qubit, but so this I work with postdocs and students who make qubits. It's pretty standard thing to do. You just need a very nice, clean facility, like a nanofab facility, to make qubits. In Chicagoland area, there are many facilities, like, you know, in University of Chicago, there is that nanofab facility that we have used before. So making any qubit is not too hard if you have a recipe. By recipe, what I mean is, if you know the fabrication parameters, like, you know, you have to tweak the properties of this superconducting circuit certain way. So you need some sort of recipe for it to be a qubit. So it's not actually hard to make any qubit, but to make a good qubit meaning it has to have very specific properties for doing quantum computing or sensing, that is hard. And so you cannot make it in definitely like, if you just start from scratch, you don't know anything about fabrication, you definitely cannot make it in a couple of days. But if you have a recipe, if you have some guidance, you can make it probably in a few weeks, or you are able to make it and characterize a little bit in a few weeks, I'd say.
Got it. So you need a good recipe and you got to be a good cook.
Yeah.
Awesome. Well, we're going to pivot a little bit back to your work and your field. And this person asks, what are you hoping to see happen in your field within the next 5 years?
Yeah. So my main interest in this field comes from doing fundamental science with quantum technology, right? So I got into this field because I was working in this dark matter experiment, and that is looking for these dark matter particles, one type of dark matter particles, and it was one of the it was the like sensitive dark matter experiment for this particular type of dark matter in the world. And still we were limited by certain things. We were limited in the sensitivity of how well we can measure dark matter, or like how well of a sensitivity we have to see the dark matter. We were limited on that. So that's when I got into quantum science, because quantum science increases the probability of seeing this dark matter, because we have better sensitivity than the existing experiments like the one I mentioned. So I would really like quantum science to advance enough that we can utilize this technology really well and discover this dark matter. So that's kind of like the main main hope, or main expectations I have from this.
Got it. And another curiosity question, but if we do detect dark matter within the next 5 years, like what would that how would that change what you do in the lab? Like, would that sort of like break everything?
Yeah, so I'll be out of job. No, just kidding. So well, am I kidding? So yeah, if we discover dark matter, then that will be revolutionary, right? Like that's like one of the biggest questions that we have so far. So that would be incredible. We'll immediately, being the scientists we are, we'll immediately try to find what next, right? Like we'll try to do what next, and then we'll immediately try to find its applications, and next science activity that we'll find, we'll try to do with the information we have from dark matter. So that's kind of how I see it. I don't know if I answered your question correctly or to your expectation.
Absolutely, yeah, 100%. Okay, cool. So this question sort of is shifting towards your lab in particular, and they ask, at Fermilab, how interdisciplinary is your team? Is the main focus just physics, or does the research also require other areas of expertise?
Excellent question. This is really good. So you bring a good point that I wanted to mention, which is, so this quantum information science, or like sensing that we do, that you saw the tour of, this is a very multidisciplinary science. So even though we say it's quantum sensing, it's not just quantum information science, or quantum physics that we use. As I mentioned, there is like atomic, molecular, and optical physics involved. Like we do a lot of like superconducting technology. We use a lot of superconducting technology, a lot of radio frequency technology, microwave technology. We use a lot of cryogenic engineering, because we have to operate all the devices like you saw in extremely cold refrigerator. And so that needs very special skill set. Similarly, the microwave technology is used to manipulate the qubits, prepare the qubit states, operate the detector. So that's actually very specific set of skills too that we need. And you just can't have like random people trained in microwave, physics. And then you have, of course, like the obvious is quantum science, but then you also have the people who are working on dark matter, like astrophysics. So really, it's like 3 or 4 or 5 disciplines that you have to deal with, or like you have people. Sometimes not everybody is going to be trained in like all these 3 or 4 disciplines. So we have people from maybe a couple of people from like one of these disciplines, and then a couple from another discipline. So you're right, like we have a very interdisciplinary group. And what ends up happening is we do some sort of like internal training and workshop, and then we kind of try to bring everybody up to date with the minimum level of all this interdisciplinary information. And we go from there, and then we build our group like that with some trainings that are relevant specifically to operate this kind of detector in this environment. And then we build the group from there.
Got it. Understood. That makes a lot of sense. I had not thought about all the different actors that you need to do what you do. And speaking of what you do, this question is in regards to, I know that the whole topic of the night was dark matter, but can quantum sensor detect other things other than dark matter?
Oh yeah. So quantum sensors can detect all sorts of stuff. Yeah. So one of the things, the previous version of like quantum science that we used was basically, I don't know if people have heard of like something called like squid magnetometer. So we have been using those. Those are like these tabletop, like very small form factor magnetometers that are very broadly used in chemistry, physics, material science, and stuff like that. So we have already like used this quantum technology in like regular day-to-day life. That's just like one example. But you can easily sense any physical property like temperature, magnetic field, anything really, like energy of like some other thing that's not dark matter. Yes, definitely we can use quantum sensing for many different broad applications.
Got it. Awesome. This is a really interesting question that is kind of out of left field, but it's really awesome. And it talks about AI, and they ask, how do you see AI tech impacting the world of quantum computing and our relationship with it?
Oh gosh, tough. Okay. So well, AI is also another one of these branches that's getting a lot of momentum. So some of it is, uh, some of it is positive, but then some of it can be a little bit, negative. So really, for quantum computing and our relationship, I guess, like there is a human component here at the end of the question. So that I'm not so sure of, but for quantum computing and other science applications, it's definitely mostly positive. So yeah, that's kind of what I would like to say.
Got it. Well, it seems like those are all the questions that we had tonight.
I have some questions from last time. Do you want
awesome.
me to go through this?
Sure. I think we maybe have time for 1 or 2 more questions.
Okay. So I had some questions that I think people this is a good one. So it says, what books, papers do you recommend to get started in studying quantum sensing and quantum sensors? So this is kind of a little bit of an unfortunate thing, because quantum sensing is extremely new field in that, like, there were some tools and technologies we're using it, but like as a field, like mainstream field, this is extremely new, and like literally things are happening as we talk, right? Like we are finding ways to use quantum sensors to do new things, like as we are talking. So and also for the reason that I said, like it's actually super into interdisciplinary science, it's a little hard at this point to write a summary overview book of like what can be done, because like we're still literally fleshing out like what can be done. So we'll have to write a book ourselves. So it looks like I kind of like thought about this and then like looked if there is anything available that is good for general public. I'd say not a whole lot. So for general public, regrettably, there's not a whole lot that's available. For us, like for academics, what we do is like the most efficient and most resourceful places to just look at the new publications, like scientific publications and summary and reviews of different relevant branches that fit in this like more interdisciplinary quantum sensing we talked about. So we just like kind of cherry pick like, okay, here is this like superconducting technology that's happening. Here is like progress in like microwave technology. Let's just like merge this, and then what can we do with this? So our thought has been very much like very technically focused, selection of scientific papers, and then synthesizing that to get things done. To summarize, for general public, I think we'll just have to write our own book and like make it available. Unfortunately, there's not a whole lot that I can recommend at this point.
Got it. Any other questions that you had?
Yes, so I had people ask me, let's see. So they wanted to know job perspective. I think this is really useful. And so maybe this is a last question that ties up our discussion today. So quantum information science in general has a very good job perspective at this point in time, because it's new and it has a lot of potential in terms of applications in many areas of science and in day-to-day life. This is a very broad topic, right? Like quantum information science includes quantum computing, quantum sensing, quantum cryptography, quantum materials, quantum algorithm, quantum teleportation. So if you work in this area in general, you're going to have, probably low risk of not getting a job either in academia or industry or some other places. So I'd say the job perspective depends on your exact expertise. Like, for example, if you end up doing like computation, definitely you might have a good shot in industries as well as national labs, maybe even like in academia. The hardware part, if you have expertise in something like that, like quantum sensing, you also have a really good shot in working in, let's say, like industries like, IBM, Google, Microsoft, all these places want quantum computers now. So if you get training in anything like this, you are like, you have really good job perspective. I know of people like engineers with undergraduate degree or master's degree, get jobs right off the bat that pays them really well in industries. And you can also go to academia, so if you have like a PhD in quantum information science, I know recent graduates who go on to work in high paying jobs in industries or like get a postdoctoral position in a very prestigious place. So right now the demand is much higher than the supply. So it is not a problem to get a job. And the thing is, many places are offering graduate programs in quantum computing and perhaps even sensing. Not a whole lot in sensing yet as a field, but in research, you kind of like focus on that quantum sensing part. But I know, like, for example, IIT, we are trying to do graduate program in quantum computing. We have a class that is applicable for undergraduates, and also like early graduate students can take this quantum computing course. So a lot of places are offering these kind of courses. So I'd say there is a really good job perspective if you have a degree or experience, hands-on experience in quantum information science.
Got it. So
Yeah.
hot field, it's time to get into it right
Yes.
now.
Good time to do this. Yeah.
Definitely. Well, Raksha, thank you so much. You have been so wonderful to work with, and this video was made possible in part or in a huge part by you. So thank you so much.
I mean, you did the majority of the job. So I would like to thank you too. And thank you everybody for listening and asking me these really interesting questions.
Awesome. Thank you.
Thank
All
you.
right. Well, everyone, thank you so much for sticking around to the end of the video and the end of the Q&A live stream. To support more programs like this one, please donate at c2st.org and consider giving $15 in celebration of our 15th year, but now it's actually 16th. Sign up for the weekly C2ST newsletter to stay up to date on what's happening in STEM. Again, thanks so much for sticking around to tonight's program. We really hope you learned something new. And now comes the really important part. If you enjoyed what you learned and what you just watched, please like this video and subscribe to our channel. You can even hit the bell icon to be notified when new videos are uploaded. And if you really, really like the video, leave a comment below. Thanks so much for watching, and thank you for joining us tonight.
Thank you. Bye.